I actually like this. All right, good afternoon, everybody. Homework 4 will be posted tonight after the session. It's on some topics that we haven't covered yet. So it's due in 2 weeks, but I may extend it depending on how fast we move through the material. So the due date is a little flexible. We'll see how it goes. There's a few problems I think you can probably tackle conceptually pretty much easily. But some of it is more focused on atoms, and we haven't started talking about atoms yet. So again, if we find that we're moving too slowly, I'll extend the due date. The homework is interesting, some interesting problems on there, some thought problems. Not nearly as much unit conversion as this last homework. Slightly different type of calculations you're doing on here about atoms. We'll see how it goes. And again, I'm more than happy to change the due date if we feel like we're not making enough progress. That being said, I'm going to start talking about our new topic today, which is going to be the hydrogen atom. We're going to start our efforts to be able to describe quantitatively everything about the hydrogen atom, right? At least be able to write down some equations. And hydrogen is unique in that regard, in that it is, in some sense, the simplest chemical problem we can look at, the simplest atom, and it is an exactly solvable problem. What does that mean? That means that I can write down an equation for the wave function of the hydrogen atom that is exact. I can calculate any property for hydrogen that I please, calculate it precisely and accurately. It is a completely explicitly solvable problem. And unfortunately for us, it is the only exactly solvable problem in chemistry. But once you get the helium, where you have 2 electrons, you can't write down an exact wave function anymore. We'll have to appeal to approximations in order to figure out what helium looks like. But hydrogen provides us the framework for how we represent other atoms. Right? In the same sense that we represented last class the vibrations of a complicated molecule as a sum or a superposition of 3n minus 6 diatomic like harmonic oscillators. Right? We have a simple theory that we expand into a more complex theory and try to explain the complex theory in terms of these smaller parts that we do understand. We're going to do the exact same thing with chemistry, atoms and molecules. We're going to use hydrogen as our framework to understand more complex atoms. And then, of course, to understand interactions between atoms, we just have to take 2 hydrogen-like atoms or atoms that look like hydrogen and put them together. Right? So hydrogen is our framework for understanding complex chemistry. And by complex chemistry, I mean electrons. It's really what I mean, electrons. So we're going to start thinking about electrons moving around nuclei now. And then we're going to really focus on that problem and understand how electrons work. Once we understand how they work, then we can start putting them in more interesting situations using the hydrogen as our framework. But we don't have the tools yet to really fully appreciate the hydrogen atom itself and the challenge that it presents. So we're gonna take some time and tackle that problem, the hydrogen atom. And the hydrogen atom presents itself in such a way that we can actually split the problem into 2 distinct parts. I'm going to identify those 2 parts today, and we're going to start working on one of the 2 parts. Right, so we'll basically sketch out the problem we need to solve, and then we'll start kind of building up our solution in little increments. Right? And basically, it'll be 2 halves to a whole, 2 different types of problems we need to resolve. We'll resolve each one individually, and then put them all together at the end. Right? And this is the way we always tackle this problem. So let's look at what a hydrogen atom is. Let's set up the problem we need to solve. Right? And by problem, I mean, we have a model system that we want to calculate wave functions for and energies. Right? We want to do quantum mechanics. So let's go ahead and think a little bit about the hydrogen atom. Right, hydrogen atom has 2 constituents, 2 components, 2 parts. physically two parts to the hydrogen atom. Hydrogen, in some sense, is just two things put together. One, of course, is the nucleus, which is a heavy, massive, positively charged particle. Okay. And of course, in hydrogen, the nucleus is very simple. In regular hydrogen, hydrogen 1, right, the nucleus is just a proton. Just a proton. There's a proton in the center. All right. I'm going to go ahead and let's write down the mass of that proton. This is a number that maybe you've never thought about. Might be worth thinking about the different masses of these objects. The mass of the proton, which we write m sub p, is defined to be 1.672, 6 roughly, times 10 to the minus 27 kilograms. Right? It's not too hard, but that's almost an AMU. It's about 0.95 AMU or something like that, right? The mass of the majority of the mass of the hydrogen atom is proton, right? Remember the mass of a hydrogen atom is 1.008 AMU. So most of the mass is just the proton. We can convert that to AMU if you want, but it's not a big deal. Right. Almost an AMU. And then, of course, there is in some sense, depending on who you ask, the more important part of the hydrogen atom, which is its electron. Right, which is a light, and it has no shape. It's a point-like particle. Right, we discussed that a long time ago, that electrons don't have any shape. Particle with a negative charge. And again, I apologize if this sounds completely trivial to you, but it's important to be explicit about these things. Right. And in 1H, the electron, which I write E minus always, has a mass it's a lot smaller. (9.1094) times 10 to the minus 31 kilograms. All right, so that's almost 10 to the minus 30. All right, so if this is 10 to the minus 20 and this is roughly 10 to the minus 30, right, the mass difference is about a factor of 1,000. I think that's an important thing to realize. That the proton is significantly heavier than the electron by a factor of 1,000. That's going to play a big role in our analysis of this problem. But what we have is a really, really big mass that sits in the center. We're going to think about it as this proton sits in the center of the atom, and we have this electron effectively orbiting proton. Right? This idea of orbiting. We're going to have to define orbits very precisely because they don't really orbit per se. But you have that kind of general idea that the proton is like a sun. You know, this is that old Bohr radius, the Bohr model of the atom. Bless you. Where you have a proton in the middle of your solar system, you have these electrons in stable orbits around the hydrogen, around the proton. I've seen this design for an atom before. It's not accurate, but it gives you a good idea, kind of classically, of what's going on. We have this light particle orbiting a very heavy one. Okay, so let's set up this problem in three-dimensional space. Again, we're going to have to represent the system mathematically in some way. So let's come up with a way to describe this system in terms of mathematics. What I'm going to do is I'm going to embed a three-dimensional coordinate system, X, Y, and Z. And I'm going to place the proton at the origin. Right, it's at the origin. And at some distance away from it, somewhere in space, is an electron. Right, so I'm going to take a vector in the center of the proton and point it to wherever, and I'll call it R, vector R. You have some electron here, right? And that R points to wherever that electron may be in XYZ space. So we have to think a little bit about what are the forces acting on this electron. Remember, again, so whenever we set these problems up, we have to remember ultimately we have to define a kinetic energy and we have to define a potential energy. So again, the electron has some kinetic energy around the system. We'll analyze that. Okay, when it orbits, it has some orbital kinetic energy, but there's also some potential energy in the system. Let's identify where that potential energy comes from. And of course, the big point, and this is the change, this is the, in some sense, the new feature of this model or of this toy problem, if you will. It's not really a toy, it's a real hydrogen atom. That we haven't experienced before. We have charged particles, right? So we have two particles and not only are they charged, but they're different charges, right? They're opposite charges of each other. There's going to be an electrostatic force between them at all times, right? There's some attraction between opposite charges, right? That attraction always exists, right? So now we have this new potential energy in some sense. No, not even in some sense. We have this new potential energy we haven't considered, which is the electrostatic attraction between the proton and the electron. Let me find my notes for this. Where the hell are here they are. Yep. So what are our potential or energy sources? Well, one is the electrostatic potential energy. And that has a well-defined function for its potential energy. It's something that you learn in electromagnetism. Says the potential energy for two particles that are of opposite charge, a proton and electron. The potential energy is a function of their distance r, is minus e squared. These are numbers I'll have to define in a second. 4 pi epsilon naught times the distance r. Let me color r. Right, so, right, and e squared, let me say e here. This is the charge of the electron. Right, and it has a well-defined value. It's a constant. Charge of electron. We also call this the fundamental charge. If you guys remember electrochemistry, there's this thing called the Faraday constant. That's the molar version of this number. The Faraday constant is the amount of charge contained in 1 mole of electrons. And so E is just the charge of a single electron. It's 1.60818 times 10 to the minus 19 coulombs. Charge of the electron. And epsilon naught is a number you've maybe never seen before, but it's an important number. It's what's called the vacuum permittivity, which basically specifies how able the empty space between the two charges is able to conduct the electricity between. And there's going to be some force that's moving through the vacuum between the electron and proton, right? And there's only, in some sense, charges are only so effective if you have a voltage or some potential difference between two charges. The vacuum is only so able to conduct the field between them, conduct electricity, if you will, between negative and a positive charge in vacuum. Right? So if you had a material, what we call a dielectric, say something that's conductive, the permittivity is very high. It's very easy to flow charge from the negative to a positive, the anode to a cathode. But now we have a system whose dielectric is the vacuum. So that charge has to be distributed from the negative to the positive through empty space. And empty space, in some sense, has some resistance. It has some, it's not perfectly capable of being able to conduct electricity 100% efficiently. It provides some resistance. So the permittivity specifies how able the empty space between the proton and the electron is allowed to carry that force. Right? There's some drag in some sense, right? It's not a perfectly conductive material. So E naught measures the permittivity of what we call the permittivity, which is the ability for the vacuum to physically move charge or electrical current from one position to another through space. And it's just a fixed number. And it's 8.854 times 10 to the minus 12. And it has some strange units. Let me give you the proper units for it. It's called a farad, F per M, farad per meter. All right, and again, the whole units, E squared over epsilon naught times R will give you something in joules. Okay, so once you take the square of a coulomb and divide it by this farad and work everything else out, you get joules out. Okay, so that's the net result of this is joules. It's just some electrostatic constants. All right, so the potential energy has something to do with the amount of charge, right? How much negative and how much positive charge you have, right? Remember, the electron has the same amount of negative charge as the proton has positive charge, right? They're the same charge. They have the same amount of coulombs in some sense. So the total attraction is the square of the charge, because you have two particles. It's the charge of the proton times the charge of the electron. That's E squared. And it's modulated, renormalized, it's dampened by the fact that the system, by the fact that the vacuum is unable to efficiently transfer energy electrically between two charges. And it has a function, it's a function of distance, 1 over distance. All right, so in general, though, what do we notice about this? This number is always negative, right? And of course, we know that because positive and negatives always attract, right? They always attract. So this potential energy is always negative. It's always attractive. So what that means is that no matter where the electron is, it always feels a force that's pulling it towards the proton. One of the things that you can calculate, again, just kind of make a note here, that the force exerted by the electrostatic potential is minus the potential, the derivative of the potential, which is proportional to 1 over R squared. Right? So that means that there's always this pulling force acting on the electron, trying to pull it towards the proton. And it's a function of R squared. Right? So there's always this kind of net force pulling on the electron towards the proton. Pulling it towards. Now here's the problem. Right? This should already give you pause. And the reason why is that this potential basically says that the attraction between the proton and the electron gets better and better and better the closer they are together. Right? So if I were to say, for instance, I place a proton in the middle here, let's pretend these are classical balls of charge. Right? We're not doing any quantum mechanics yet. So I place this proton right in the middle at rest. Right? And I bring an electron in. Right? What does the electron do? Well, the electron feels that force from the proton, and the proton sucks it in. Right? The force is always pointing towards the proton. So as a function of time, that electron is going to get closer and closer and closer to the proton. Not only that, it accelerates. As it gets closer and closer, the force increases. Right? Remember, F equals ma. So as the force increases as it gets closer, it accelerates. So as the electron gets closer and closer to the proton, it's moving faster and faster towards the proton, right? So what's actually happening is all I've created in some sense classically is an electron vacuum. Right? The thing that this is going to do classically is the electron's just going to get sucked in by the proton. Right? That's the most stable arrangement. Where systems always want to go to the most negative energy. So the most negative energy you can get is where that electron is infinitesimally close to the proton. So we would predict that hydrogen atoms classically don't even exist, right? Because the dominating force is this electrostatic force, which wants these two things to be close as possible. So technically, if there was ever an electron or proton nearby, that proton's just going to suck up that electron immediately. Right? So hydrogen atoms shouldn't exist at all. No atom should. No atom should exist at all. All positive charges should be canceled out by negative. But we know that that's not true, right? Because we have hydrogen. And what do we see in hydrogen atoms? Well, just like what Rutherford shows us, Ernest Rutherford shows us with his gold foil scattering experiments, is that there's this positively charged core in an atom, and there's a bunch of empty space, and then suddenly there's a ring of electrons. There's some shell of electrons that deflect particles on the outside, and then there's a bunch of empty space, and there's a proton in the middle. Right? So what we see in experiment is exactly what you know, which is that these electrons exist at some distance away from the proton, some finite distance, and they're perfectly stable, right? They're not constantly collapsing like a black hole. All right. So there must be some sort of force that counteracts the electrostatic force, right? There has to be something that balances it. Right? There has to be something acting on it in this direction, or in some perpendicular direction to the electrostatic force, that causes it to not get sucked in like a vacuum. Right? That brings up our next source of potential energy, which solves this problem. At least we think it does. We'll have to look at it more carefully. So our other force, there must be some other force. And the other force is the fact that this electron is orbiting the proton. Let's make an assumption that it's moving around the proton. So imagine this electron has some angular momentum as it orbits the proton. We have it in some sort of orbit. Right? What happens in terms of forces when you have something rotating around the central object? What is that? Well, that's think about when you're spinning something, right? You know, like the classic physics example of when you stand in those spinny rides and you stand against the wall, and it spins and holds you up against the wall. Have you guys ever seen those? I forget what they're called. Right? There's this force that as you spin, the force that's being applied towards the wall, pressing you against the wall, and you're rotating this way, and it's forcing you out this way, right? There's this centrifugal force that's pushing you away from the center when you spin, right? So there's going to be some centrifugal forces from the orbit. Right, so let's do a little bit of analysis of the centrifugal force. Let me get my right notes for this. Jumping around a little bit. So let's think a little bit about angular momentum. So angular momentum is a vector, which we call L. And it's defined as the displacement vector R cross product with the momentum vector of the object. And another way we could write this is M, the mass of the object, so that would be the mass of the electron, times the displacement times the velocity vector of the system, right? Because P is equal to mv. Okay, so what we have now, let's look at our problem here, our coordinate system here. All right, we're going to apply, so we have R, we're going to apply some momentum in some direction around the proton, right? So let's say, for instance, I'm pushing the electron in this way. All right. So I have a displacement here, and I'm making again, the idea is I'm attached this electron to the proton, so it's at fixed distance, fixed R, and I'm applying a momentum at fixed R in this direction, right? And the angular momentum is the cross product of these two vectors, right? We're going to use the right-hand rule for this. Let's see if I can do it. I always forget how to do this. So we have the vector this way, momentum is coupled in this direction through my fingers, and that means the angular momentum is out of the board. Yes, the right-hand rule. And so we have an angular momentum vector. I don't know how to draw this. Out of the board like this. And what that means is that this electron with this motion is orbiting in this direction. Right. So the angular momentum vector is out of the board. That means that the system instantaneously is leaving the board, and it's in a circular orbit or some sort of orbit. So it means it's moving in this direction, in a clockwise way. So what this is doing now is orbiting everything in a clockwise direction. So at fixed R, application of momentum in some direction leads to an orbit with a tangent momentum Okay. So we're going to apply this, right? So we have this force, and this thing is orbiting in this way, right? So it has some kinetic energy from orbit, and that's in some sense acting against the pull, right, of the electrostatic force, right? This is pulling, the electron is being pulled away from the proton, but we're applying a kinetic energy to maintain a certain speed, certain angular frequency, some orbital speed at fixed distance, right? So what's happening then effectively relative to the proton, there's a net force in the opposite direction resisting let me do a different color. There's a net centrifugal force resisting the pull of the electrostatic potential. Okay, so in order to maintain a stable orbit of our proton, we have at some distance r, of our electron at some distance r, we have some resultant potential energy from the vacuum effect, right? The attractive effect between the negative and positive charge and potential energy. And in order to counteract that, we need to induce kinetic energy, angular kinetic energy, that's equal and opposite to that potential energy. Right? So the total, in some sense, right, the total angular energy, the energy of rotation, needs to be equal and opposite to the potential energy of the electrostatic potential. All right, so a stable orbit is maintained when angular kinetic energy is equal to electrostatic potential. Absolute value. Absolute value, because one's negative and one's positive. It's absolute value, right? So we need to cancel each other out, right? The idea is that at some distance, we need to make sure that electron is spinning fast enough so that it doesn't get sucked down into the void that is the proton. This is exactly the argument that Niels Bohr came up with. Come up with that classic example of the hydrogen atom as being a proton with these concentric stable orbits of the electron. Maybe you've seen this, right? This design, right? The result of these physics leads to what's called the Bohr model, which is that you have a proton in the middle, and the electron, in some sense, has these stable orbits around the proton, which are labeled, right? Which have numbers, right? So there's an n equals 1, there's a 2 orbit, a 3 orbit, and so on and so forth, right? N equals 1, n equals 2, n equals 3. Right? I'm sure you've seen these models before. How Niels Bohr came up with the description of the hydrogen atom, saying that there has to be stable orbits that are quantized that exactly cancel out the potential, the electrostatic potential energy. Here's the problem with Bohr, as we're going to find out with Bohr's model. What does this require? Well, this requires the electron to always have angular momentum, right? No matter what, right? Even in the ground state, even in n equals 1, electron must have angular momentum. Right? If it had no angular momentum, it means it's not orbiting, and therefore it's going to get sucked down completely, right? That's what Bohr's claim was. Bohr actually gets, I'll try to compare to what Niels Bohr talks about. This model is fundamentally flawed in a number of different ways. It does predict some things about hydrogen, but it predicts them for the wrong reason. And the reason why it predicts it for the wrong reason is because by this argument, no matter what, the electron always has to have angular momentum. Right? No matter what energy it's at, it always has to be spinning. But guess what experiment shows? Experiment shows ground state of hydrogen right, which is the 1s orbital, has no angular momentum. So Bohr says, and there's a perfectly logical explanation, right? That you have to have angular momentum for the electron to be stably orbiting the proton. Otherwise, it gets sucked up. So in every level, it has to have some angular momentum. But in the 1s orbital, there is no angular. In fact, in all the s orbitals, 2s, 3s, 4s, 5s, 6s, 7s, all of them, there's no angular momentum. Yet they still stably exist. Right? That should be that's completely counterintuitive. I've just claimed that you have to have angular momentum to create a stable orbit, but there are stable orbits of the proton, of the electron around the proton that have no angular momentum. So obviously quantum mechanics is providing something special that we're not quite appreciating just yet. Right? There's something fundamentally wrong with this argument. But it turns out that this argument is perfectly reasonable. I mean, there's nothing invalid about the argument we just made. There's something special about when we plug all of these ideas into quantum mechanics that we get stable states where there is no angular momentum. Right? And that's kind of the goal that I want to get to show that the solutions for angular momentum of the electron around the proton gives you stable orbits with no angular momentum. There are just stable balance states of the electron around the proton where the electron effectively is not spinning. right? Those are the s orbitals. So that's going to be our ultimate goal, right? We need to explain this difference. And this difference is critical because when you have this approximation from Bohr, which is perfectly reasonable, you get some of the right properties of hydrogen, but very few of them. But the moment we make this assumption, right, when we go to experiment and say, hey, let's build a theory that explains experiment, we get an exact solution of the hydrogen that gets everything perfectly. Right? So it's built into the hydrogen atom that there are stable states of no angular momentum. Just some magic of quantum mechanics that causes this electron that has no angular momentum, in some sense, stay away from the proton. Right? It's quite magical, and it works out beautifully that way. And I kind of want to show you some of that elegance of this without having to dig too deep into the math. Okay. Let me stop here. Any questions so far? Okay. So let's see if we can set this problem up. So as I promised, as I said, there are the hydrogen atom has two different parts that we can solve separately. And we've in some sense identified those two parts already. There's this electrostatic part, and then there's this angular part. Right? And I want to identify those more explicitly. And we're going to break the hydrogen up into those two separate parts. We're going to break it up into the angular momentum part, and we're going to break it up. We're going to analyze that problem separately from the electrostatic potential part. And we can do that, and let me explain why. So the hydrogen atom is a separable system. All right, let's define exactly how it's separable. All right, the first thing I want to do is I want to take advantage of the fact that we have this electrostatic potential, which is just a function of the distance. And then we have this angular momentum, right? And if we were to track the electron as it orbits, we're going to have to use some angles, right? The idea is that the angular part, we're going to fix the electron to some distance. So R is unchanging, but its angular position relative to one of the axes, to the axis system of the proton, is changing in time, right, as the electron orbits. Right? So there's just some angular information in the angular momentum, hence the name. So let's define a coordinate system for our hydrogen atom that takes advantage and separates the angular part from the radial part. So the idea is that electrostatics are what we call spherically symmetric. Only dependent on distance, not angle. Okay, and again, that should be easy to see. If we have a proton in the middle, and we put the electron at some distance r, and we cause that electron to orbit, or sorry, and this has a potential, sorry, let me say this, right? And the potential here is V of r is equal to minus e squared over 4 pi epsilon naught r. It doesn't really matter what angle relative to the z-axis, they label that, to the axes, where the electron is. Right? It's angle independent. Right? So if we ask the question, what does the surface look like of all the points the electron can sit at where it has the same potential energy? It's a sphere of radius r. Well, I can kind of draw that, if you will. See how well I can draw this. Well, I've got this sphere of radius r. right? Where V is the same at every value. At radius R, right? That's what we mean by spherically symmetric. It doesn't matter what angle. With an angle, you have a sphere of constant values. Right, so this is only, so in some sense, the physics of the electrostatic potential are only one variable. It's a one-dimensional problem. So what about the angular momentum? Well, angular momentum is at fixed R, but depends on angles. Right? So we can define another coordinates. We can define our coordinates now. In the way that you would define them in Calc 3. We have an electron here at this point, R. Right? We can define an angle theta between the z-axis and R. And then we can define another angle between the x-axis, which is phi, the xy plane. So angular momentum is just a function of theta and phi. Right? It's a 2D problem. Right? So this is why I'm saying that they're separable problems. The electrostatic potential is only dependent on R. The angular momentum is only dependent on the angles of the vector in the space. So all the physics that happen along R are independent of the physics that happen along angles. Right? Very, very kind of logical thing, right? So we're going to separate the two parts. We're going to do the radial part separately from the angular momentum part. And what we'll do is at the end, when we both understand both of these problems, we can put them together into a combined solution that accounts for the physics of all the coordinates and get a full picture for the hydrogen. We'll literally take a product of these two solutions, and that product will be our solution for the hydrogen. We're not quite there yet, but we will get there. So what I want to focus on today is this angular momentum part first, right? It's the easier of the two parts. Right? The physics of angular momentum are really, really, really simple. Deriving them is not simple. We're not going to derive them in this class. We'll set up the problem, and I'll just give you the solutions. And then next class, we'll kind of talk about them in more detail. So let's tackle this angular momentum problem today. The angular momentum of the electron around the proton at fixed distance. Excuse me. Okay. All right, so let's set this problem up like this. So we're doing angular momentum. All right, so let's set up this problem in like a more harmonic oscillator style way. So we're gonna have two masses. We're gonna have the proton, and it's connected to the electron. I'll make the electron yellow. And it's connected by a fixed bar with length r. Okay. All right, and we're going to spin this system. All right, we're going to spin the two particles, right, consecutively or coherently together so that they spin on their axis. I have a beautiful picture of this. I'll draw for you. So we're going to spin these. I'm going to define a center of mass for the system, right? Remember what the center of, right? We have where's the center of mass in this system? Well, we have a mass that's about effectively a mass of 1,000 and a mass of 1 comparatively. They're about 1,000 part difference. So the center of mass is in the proton, right? So this system is just lumpy. So the center of mass, we'll say, is right here. Right, so this doesn't really, right, this isn't like a diatomic molecule where the center of mass is right in the middle and the thing spins like a barbell floating in space. Rather, the way that this spins is in some sense, you're holding that proton in place and swinging the electron around it, fixed spot. So in the center of mass frame, the proton does not move. So effectively, we can say that since MP is so much bigger than M sub E, the center of mass is in the middle of the proton. So what we can do then is put the center of mass in the middle of our coordinate system. Here's our proton. All right, and we extend from the center of mass, from the center of proton to our electron at some distance r. Distance r. And we're going to spin it in some angle. We're going to spin it in some direction in this way, right? So we have this, just let the electron orbit around in this direction. Yeah. Okay. And so now what we'll do, we'll ask the question, well, so this again will have, right, as this rotates, right, this is going to have some net momentum. It's also going to have some frequency of rotation. Right, so imagine it rotates at some frequency omega. And this is in radians per second. Right, this is the angular frequency. So it's how much time it takes to go 1 radian. Right, and the velocity of the atom, right? So the velocity of the electron is 2 pi sorry, no. Take that, get rid of that 2 pi. I apologize. Is so this is in hertz, omega over 2 pi b. Yeah, sorry, it is 2 pi omega times the distance between the electron and the proton. Oh, no, sorry. Get rid of this. All right, it's not there. Omega. Omega rot times the distance of the proton, right? So that's the velocity of the electron. And so we can write the kinetic energy of it. Kinetic energy which is 1/2 the mass of the electron times the velocity of the electron squared. Right? That's going to be 1/2 m sub e r squared omega squared. And we're going to define a new parameter now. Define what's called the moment of inertia. I, which is MER squared. And this says, therefore, that the kinetic energy is 1/2 I omega squared. And then by using the fact by the definition that angular momentum, definition of angular momentum, let me just make sure I get it right, is I times the angular frequency, then we can write that the kinetic energy of the system is the square of the angular momentum divided by 2I. Okay, so the kinetic energy of this electron is proportional to basically the magnitude of the angular momentum. It has nothing to do with the direction, just how fast you're spinning it, right? Make a squared, right? How fast you're spinning it, instantaneous angular frequency or velocity of the system, divided by how much mass you're swinging through space. So I can kind of say, right, this is, again, kind of looks like, in linear terms, p squared, right? The linear momentum divided by the 2 times the rest mass of the system, right? So the moment of inertia in some sense is what we call the rotational mass or the inertial mass of the system. All right, it's just some effective mass, which has something to do with the actual mass of the system plus its distance. Some inertial, we call this a rotational mass or an inertial mass. All right, so angular momentum and regular momentum really aren't that much different. It's just that one's in an angular form and has a slightly different mass. That's distance dependent. And then L squared looks a lot like P squared. More the faster you rotate the object, the more kinetic energy it has. For linear motion. Okay. So what we want to do now, right? We have a kinetic energy for the angular momentum, right? It says that if we spin it up to some omega, and we have some mass, then the kinetic energy is L squared over 2pi. And again, maybe it's worthwhile to think about how moments of inertia work. Right? The best way I like to think about moments of inertia is to think if you fix something with fixed mass, right, and you give it some initial momentum, right? I give it a push. Let's see if I can do it in the chair. See if I can do a fun demonstration for you. This chair doesn't spin enough, Dan. All right. Now let me describe it to you, right? So let's imagine you take a figure skater, right, and you give them a fixed force. Okay, so imagine you have like a mechanical kick that you give them that has a fixed amount of force that is applied to the skater, and the skater's going to do some turny, twisty things. I forget what they're called. It's going to do it. Not a jump, but they're just going to spin on one like this. All right, and so I'm going to fix L. I'm going to fix L. I'm going to give it some fixed momentum. Right, and so depending on the size of the skater, right, which sets I, the mass of the skater times how big the skater is around its rotational axis. If the skater is spinning along this axis, then its moment of inertia is proportional to this length, how much it extends out this way. Fixed momentum, right? So if I have a small I, right? If I have a small I, which means my arms are closed, what does the skater do? Does the skater rotate fast or slow? Fast, right? And what happens as I open the arms? Slows down, right? Okay, very simple. Right, so the kinetic energy, therefore, you give it fixed amount, and as you start to increase their size, their kinetic energy drops, right? Because their velocity drops.
Professor Green doing that?
Oh, okay, yeah, there we go. Yeah, yeah. So maybe I can show that next time in class or something like that. Yeah, please do. So anyway, I'm sure everyone has seen this demonstration before, right? But this is the exact same idea. Okay, so we have this kinetic energy, right? Well, what can we do with kinetic energy? Well, we every time we get a kinetic energy function, we measure the kinetic energy, we can promote it to an operator and solve find the wave functions for it, right? Remember when we got the kinetic energy for our particle in a box or stretching potential, right? We promote it to operators and we solve for the wave functions. Right? So we have this kinetic energy. So now what we have to do is figure out what are the wave functions that satisfy angular momentum. So this is reduced now to an angular momentum problem. All right, so the idea is we're going to do quantum mechanics and promote T to an operator T hat. And T hat we're going to have a new operator for L, which we square and divide by 2I. Well, we know what kinetic energy is. Kinetic energy in operator also is equal to minus h bar squared over 2 mu times d by dx, second derivative, right? But remember, this is a three-dimensional problem, 3D problem. So we need to also consider motion along y and z as well. So the kinetic energy operator is just a sum of the second derivatives with respect to the wave function, the second derivatives with respect to all the directions. Right? We can see that there's a relationship that we can compare here between this equation and this equation. Right? It kind of looks like L is proportional to minus h bar squared times this thing right here. And so by just making a substitution, we can say that the kinetic energy from angular momentum is minus h bar squared over 2I times d squared dx squared plus d dy squared plus d squared dz squared. Well, that's nice. Sort of. The problem is that x, y, z's are really miserable coordinates for us here. We're dealing with some of angles, right? So we're going to have to track. We don't want to track angles in terms of x, y, and z. That is such a miserable way to do trigonometry. Right? We're looking at something that's moving in a circle. Even still, this also doesn't take account of the fact that the system isn't moving in terms of its distance, right? R is fixed. So what that means is that the square root of x squared plus y squared plus z squared, which is the length of R, the displacement from the origin, that quantity never changes. So there's certain motions along x, y, and z that you can do that don't change the physics at all, right? The ones that maintain the distance, origin. Physics are the same everywhere because it's a function of R. So we're not taking account the symmetries of the system, the angular and the radial symmetries of the system by doing x, y, and z. So we're just going to get rid of x, y, and z. We're just going to remove it from our mind and change to a different coordinate system. And what that's going to do is make our equation a little more complicated. We'll see for our Hamiltonian, for our wave function equation. But it takes advantage of the symmetries of the problem, which is what we really want. We want to think about things that are in angles, but have no change in R. All right, so we're going to convert to spherical coordinates for the hydrogen atom. So let me just remind you the coordinate conversion between spherical coordinates and Cartesian coordinates. We'll take a test point here. And this is at x, y, z. It has some distance r, some angle between theta, z and r is theta. And then there is this, if we project r on the xy plane, we have this angle phi, which again tells you which way R is pointing in the XY direction. Right. So just a reminder, theta tells you how close it is to Z or minus Z. Right? It swings out this way, and phi it rotates you in the perpendicular direction. Okay. Just as a reminder. So let's do some conversions really quickly. As I said, R is just this is the length of the vector, which is the square root of x squared plus y squared plus z squared. And of course, R can be any value between 0 and infinity. It's an infinity. Theta is the inverse cosine between Z and R. Right, and theta tells you which way you're pointing along Z. So Z can vary, right? The pointing along Z can vary from plus Z to minus Z. Plus Z gives you a theta of 0. Minus Z gives you a theta of pi. Theta is defined between 0 and pi. Inclusive. And then phi, of course, is the inverse tangent of y over x. Oh, I see what I did wrong. Sorry, that's not right. Phi is here. It's theta y over x. I gave you x over y instead. That's also fine. Phi. That angle instead. And it can be between 0. I'm sorry. This is phi. And 2 pi. Right? Anywhere along the xy plane. Right? So 10's a circle. Okay. So those are our 3 coordinates, right? We can always interconvert between them. And this leads to x is defined as r cosine phi sine theta. Y is r sine phi cosine theta. Or sorry, sine theta. I apologize. Yeah, sine theta. Do my math right. And z is r cosine. Okay. So in order, right? So we now have a one-to-one conversion between every point XYZ space with a series of 2 angles and an R, right? It's a complete one-to-one conversion. So any XYZ can be represented by a unique set of angles and a distance. And so we want to do all of our physics in R, theta, and phi, right? And that's really, now we're taking advantage of our symmetries, right? Because our angular momentum is only going to be a function of theta and phi, because it's a fixed R. And then theta and phi don't matter for the electrostatic potential because it's spherically symmetric. So now what we've done is we now have a coordinate system that works perfectly for our problem. We can split it down the middle, put the radial problem separately, the function of R's, the physics along R can be its own function, it has its own coordinate, and then the angular momentum has its own set of coordinates as well. Right? So we can take advantage of all the symmetries of our problem in spherical coordinates, which is why we switched to it. Notice that if I keep it in x, y, and z, right? In some sense, the motion along theta and phi is a function of x, y, z, r, x, all of the motions are coupled along x, y, and z. And so you got to keep track of everything. It's really, really nasty. X, y, and z, everything is coupled. But in spherical coordinates, we uncouple the 2 motions, the 2 physics of electrostatics and angular motion, right? Just naturally, it just comes out of the math. So that's a really nice thing to take advantage of. The problem is now we have to do a coordinate transfer, coordinate conversion of our operator from x, y, and z coordinates into r, theta, and phi. Right? So in order to convert d, like say the second derivative of x, we got to take 2 derivatives of this function. Right? And then we have to take 2 derivatives of this function and 2 derivatives of this function. and then arrange everything in terms of r terms, theta terms, and phi terms. Right? It's a lot of math. It's quite a bit of math, and it makes it more complicated, right? We're going to have some terms that are dependent on theta, some terms dependent on phi, some dependent on r, but it's not going to look nearly as clean as this. Because we're going to take some products. We have some product rules in our derivatives, some chain rules that we have to do. It's going to look kind of nasty, but it takes advantage of the symmetries of our problem. All right, so let me write down what it looks like. And then we'll just kind of look at the math really quickly. And then starting next class, we'll look at the solutions in depth for this. All right, so we're going to take the second derivatives with respect to the coordinates. And we're going to convert into spherical coordinates. R, theta, and phi. And we get three terms, right? We get a term proportional to dr, a term proportional to d theta, and a term proportional to d phi. The r term is 1 over r squared times the derivative with respect to r of r squared times the derivative with respect to r. Right. So the way that you would calculate, say, solve a wave function, solve the equation for this, is you would put a wave function in here. This is an operator. You'd have d psi dr. So you would calculate the derivative of psi, multiply that derivative by r squared, and then take the derivative of that product, and then divide the whole thing by 1 over r squared, right? We'll work from right to left when I evaluate this. And so even though this looks nasty, I mean, if you kind of zoom out in some sense, right? If everything is really, really clean and you have a perfect function, in some sense, this r squared is canceled out by this r squared. And I effectively have the derivative of r times the derivative of r, which is the second derivative of r, right? Which is kind of what we want, right? We know that this is second derivatives with respect to the coordinates. And this kind of looks like the second derivative of r, right? With some funky r's on the outside that may or may not cancel each other out. Okay. In fact, they don't usually cancel each other out because, again, the derivative of this interior is going to have a product rule. You're going to take the derivative of this times this plus this times the derivative of this. So the r squareds aren't going to necessarily cancel out, but they kind of look like they do. Right, so this is the radial term. Right, and then there's the term in terms of theta. It's 1 over r squared sine theta times the derivative with respect to theta of sine theta d by d theta. Right, this is what we call the azimuthal term. Azimuth is in astronomy, the azimuth is the highest point, the most vertical point in the sky. Right, so you can think about the z-axis as the azimuthal direction. So that's where that term comes from. So the z term, in some sense, the z angle. And then there's the other term for phi, which is 1 over r squared sine squared theta d squared d phi squared. And this is the other. So this is the, I forget what we call this extra angle here. This is the other angle. I'll just call it the phi term. This is the XYZ motion, XY point rotation. All right, but in general, right, these terms, they look funky. And these funky extra terms that come out of this equation are just come from the chain rule and all the unit conversions, or not the coordinate conversions. Right, you've got a bunch of sines and cosines and things like that, and r's, so things come out. But in general, right, it kind of looks like the second derivative with respect to r plus the second derivative with respect to theta plus the second derivative with respect to phi, right, which looks just like this. Right? It's just a little extra funkiness to it. But we can already take advantage of this problem, the symmetry, because in our angular problem, in angular momentum, there is no change in r, right? We're at fixed r. Right? So this top term, the radial term, does not contribute at all to our problem. We can get rid of it completely for angular momentum. It doesn't contribute because we're at fixed distance. Right? So I can just get rid of this completely, right? So that's really nice, right? I couldn't do that in Cartesian coordinates. Cartesian coordinates, no matter how I move the atom or how I move the electron, it's always dependent on X, Y, and Z. It's always dependent on all three coordinates. But in spherical coordinates, I lose one of the dimensions completely. Right? The angular momentum is only dependent on theta and phi. So I've gained some simplicity back because I can get rid of one of the three partial derivatives in my equation. Right? So this goes to 0 in angular momentum. So our final solution, our final problem that we need to solve is for this Hamiltonian minus h bar squared over 2I times 1 over sine theta d by d theta sine theta d by d theta plus 1 over sine squared theta d squared d phi. So what I need to do are find, right? So my goal here is stable solutions, stable orbits satisfy this Hamiltonian psi is equal to some energy psi, where this is the energy of rotation of orbit. Right? So these stable orbits that we're looking for are these wave functions. These are our stable orbits. And whatever the stable orbits are, satisfy again the Schrodinger equation, the quantum measurement theorem, which says that this Hamiltonian applied to those functions that represent the stable orbits give you back that orbit function times an energy. Right? It's the same problem we solve every single time. Now it's a little more complicated, right? We have some angles that we have to deal with and things like that. All right, and so this problem is kind of tricky to solve algebraically, not surprisingly, but you can solve it. Right? This is a solvable problem. And in fact, it turns out, this is one of the cool things, is that the solutions to this problem have been known for a long time. So the wave functions, the solutions are wave functions psi, which are functions of theta and phi that represent stable orbits of some fixed angular minimum. And these solutions have a very special name. We'll show you a picture of them. The solutions are called spherical harmonics. Now I want to show you a picture of some spherical harmonics and tell you where they actually appear. They appeared hundreds of years before. We'll look at the analysis of these in a little more next class. But I'm going to show you the stable solutions. You can plot them. We'll break this picture down a little bit more carefully next time. But what we're going to find is that these are the different types of basically we're gonna have quantized angular minimum. I'll write that here. This is L. 0, 1, 2, 3, 4, 5, 6. This is the amount of angular minimum, right? The total amount of energy. And what we find is that there's a set of special angular solutions for the problem, depending on how much angular momentum our system has. All right, our system will have quantized amounts of angular momentum. You can have 0 units, 1 unit, 2 unit, just like we can have quantized amounts of vibration. And each one has a set of solutions that are allowed. Do these pictures remind you of anything from chemistry? Say again? Orbitals. Sure looks like an s orbital, sure looks like a p orbital, doesn't it? Right? S, P, D, F, G, H, I, right? These are the orbitals, right? So the shape of the atomic orbitals come from the stable orbits of the electron, right? And there is a stable solution with no angular momentum. L is 0. This does not have any net angular momentum. And we get an s orbital out, a spherically symmetric solution. So somehow in this quantum mechanics of the problem, even though we have no angular momentum, we can still define a stable orbit of fixed radius with no angular momentum that is spherically symmetric, an s orbit. And it just naturally falls out of the math from this analysis, right? And then we'll find as we excite the system to more and more angular momentum, we get these more complex structures that look like this, that have these lobe-like structures. And those correspond to the p, the d, and the f orbitals. So a p orbital, electron in a p orbital in some sense is an electron with 1 unit of angular momentum. It's actually spinning. And a d orbital is one of 2 units of angular momentum. It's spinning in some sense with twice as much angular energy as a p electron. All right, so the structure of the orbitals come purely from the angular part of the problem. The shapes don't come from the electrostatic part at all. It comes from the angular part of the problem. We'll have to think about how the radial part affects these, but we should look at these a little bit and see if we can understand all of the math. So starting next class, we'll come back to these spherical harmonics. We'll write some equations down for them, plot them, look at them. And then we also have to ask, what are the energies of these as well? Right? We have to think about the kinetic energy too. So we'll come back to that. We'll think about rotation a little bit. We'll understand the reason why the electron exists and doesn't get sucked in, right? We'll look at that problem. And then we'll start tackling the radio problem. All right, have a good one, guys.
I don't know if Ella told you, but we were able to get SAT last night.
I saw the pictures.
Okay. We
Yes.
have something down in like 400.
Yes,
but
that is just noise from the interferometer.
I thought,
So the next time you guys run it, you need to cut the minimum frequency up a little higher. Yeah, like 600 should be
Yeah.
fine. Yeah, that's just electrical noise.
yeah, the example spectra started at 800, so I was like, we definitely just need to trim it. They ended up, like, we went in and like edited the spectra after the fact, and it's fine. but-
Yeah.
Also, Teams Gorillas right now.
I know, I saw it. What's up?
Okay, so remember the issue with our data last night?
Yeah.
It got worse.
Let me get it out. Actually, so we read if there's peaks.
Okay. So what's worse?
So. I think this part right here. So when we all bring it into this.
Mhm.
The Zonner table,
Mhm.
it was supposed to be part of the.
Yeah.
But it was. It was either trying to go into the zero column or the
Yeah.
two column. And both of them were moving. The first time we did the data. It was trying to go, just one of them was trying to go into. This was trying to go from B2 to B1. When I had been reset the averages from B2.
Okay.
And they're like, it's like perfectly like aligned to the number in the column. So,
Just coincidentally.
yeah.
Okay.
That's okay. Or could we find out the peaks to pick or?
I need to see your whole P pick. Can I see, where do you do all your fits and stuff like that? Let me see what your results are. Oh, those are your peak. You haven't done the LinS stuff yet.
No, not yet.
Oh, okay.
It was, this is, yeah, we
You
did
need
it
to go look at Linus and see what your results are.
from the ones that we picked.
Yes.
Okay.
And then we'll
Yeah. Yeah, well, ask me again next time. Yeah. Hey, what's up, Kev?
Hey.